Welcome back. Last time we met the transistor, a current-controlled valve where a tiny base current commands a collector current beta times larger. And we packed two golden facts for the road. V sub BE is 0.7 volts and I sub C is beta times I sub B. Today we put all of that to work. Our first real transistor circuit is waiting, the fixed bias circuit, and we will solve it completely, both currents and every voltage in sight. Here is our first transistor circuit and the simplest possible way to bias one. It is called the fixed bias circuit. A 12-volt supply, V sub CC, feeds two branches. One branch goes through R sub B 240 kilo-ohms into the base. The other goes through R sub C 2.2 kilo-ohms into the collector. The emitter is wired straight to ground. Beta is 50. You also see two capacitors where the AC signal would come in and out. But remember, in DC analysis, a capacitor is an open circuit. They are there precisely to keep AC out of our DC story, so those two wires simply drop out of the picture. The question asks for I sub BQ, I sub CQ, V sub B, V sub C, V sub BC, and V sub CEQ. Now, do not let the Q scare you. Q stands for quiescent, the quiet resting point. It just means the DC operating value. Find I sub BQ simply means find I sub B. For a circuit like this, we really have one tool, Kirchhoff's voltage law. But let me teach you how to walk it, because this is where most people struggle. We start our journey at the supply, at 12 volts. Which current flows out through the 240K resistor? There's only one path here, and it feeds the base, so that current is I sub B itself. First obstacle on the road, R sub B. We pay the toll, minus I sub B times 240K, and we arrive at the base. Now, here is the trap almost everyone falls into. You feel like the walk must continue all the way down to ground, no matter what. It does not. You may stop at any point whose voltage you know. And before writing anything, ask one question. Does this line reduce my unknowns to 1? If I stop here and write equals V sub B, I have two unknowns, I sub B and V sub B. That line is useless. So what do we actually know? We know the base to emitter drop, 0.7 volts. So take one more step across the junction, minus 0.7, and now I am standing on the emitter. And the emitter is wired to ground, 0 volts. I have arrived. So the full walk reads 12 minus I sub B times 240K minus 0.7 equals 0. One unknown. 12 minus 0.7 is 11.3 volts. So I sub B equals 11.3 divided by 240K. Volts divided by ohms gives amps. 11.3 over 240,000 is 4.71 times 10 to the minus 5 amps. 10 to the minus 6 is micro, so this is 47.1 microamps. Quick magnitude check. Base currents live in microamps. 30 to 80 microamps, you are healthy. If you found milliamps, you almost certainly forgot the kilo in 240K. Any trouble so far? I do not think so. I sub B is ticked. Who is next? I sub C, and it is one line. I sub C equals beta times I sub B, 50 times 47.1 microamps. 50 times 47.1 is 2,355, so 2,355 microamps. Slide the decimal 3 places, 2.35 milliamps. And the magnitude rule again. Collector currents live in milliamps. A few milliamps is exactly what we expect. While we are here, the emitter current, beta plus 1, 51, times 47.1 microamps is about 2.4 milliamps. 2.35 and 2.4, nearly the same, just as we promised. I sub C is approximately I sub E. Now the second walk on the collector side. Again, we start at 12 volts, which current flows through the 2.2 kilo-ohm resistor. We are on the collector branch, so it is I sub C. And the beautiful part, this time we know it, 2.35 milliamps. So the obstacle, minus I sub C times 2.2K. 2.35 times 2.2 is about 5.18. And here, units take care of themselves. Milliamps times kilo-ohms gives volts directly. So the resistor eats 5.18 volts and I arrive at the collector. From the collector, one step across the transistor, minus V sub CE, brings me to the emitter, ground 0. 12 minus 5.18 minus V sub CE equals 0. So V sub CE equals 12 minus 5.18, which is 6.82 volts. Sanity check before moving on. 5.18 plus 6.82 is exactly 12. The whole supply is accounted for. Nothing leaked. Lovely. Let us take inventory. I sub B found. I sub C found. V sub CE found. Who is left? V sub B, V sub C, and V sub BC. And for these I will hand you a rule that pays rent forever. Any voltage with two subscripts is simply first minus second. V sub CE is V sub C minus V sub E. Always. Do not forget this one. So what is V sub E? The emitter is wired to ground, so V sub E is 0 volts. Then V sub CE equals V sub C minus 0, which means V sub C is just V sub CE, 6.82 volts, found for free. Same trick for the base. V sub BE is V sub B minus V sub E, and that is 0.7. With V sub E 0, V sub B is 0.7 volts, also free. Notice we never touched the circuit again. Last one, V sub BC, first minus second, V sub B minus V sub C. 0.7 minus 6.82, that is minus 6.12 volts. Negative. Should that worry you? Not at all. The base should sit at a lower voltage than the collector. A negative V sub BC tells you the base to collector junction is reverse biased. And that, together with the forward biased base to emitter junction, is exactly the recipe for the active region, the region where the transistor amplifies. That minus sign is the circuit telling you, I am healthy. Let us bring it all together. The BJT is a current-controlled valve. A tiny base current commands a collector current beta times larger. Two golden facts unlock the DC analysis. V sub BE is 0.7 volts and I sub C is beta times I sub B. The method is a walk. Start at a voltage you know, pay every obstacle on the road, and stop at any point whose voltage you know. You do not have to reach ground. For double subscripts, first minus second, always. And keep your magnitude radar on. Base currents in microamps, collector currents in milliamps. Our fixed bias circuit came to rest at 47.1 microamps, 2.35 milliamps, and a V sub CE of 6.82 volts. Next time, we put a resistor under the emitter and discover why this simple bias likes to drift and how that one resistor pins it down. See you there.